Welcome to qnawire.
Here we're going to find the electric field of a ring, kind of like a washer. And I'm showing it from a couple different viewpoints so that we can see some of the geometry going on. But we're assuming that there is a uniform surface charge density placed on the washer surface. And I'm calling that sigma for surface charge. The way we're going to work with this is we are going to use Coulomb's law, essentially. So we are going to look at Coulomb's law, which says that electric field is equal to a constant. And I'll call this little k for now, but it is an electrical constant. Maybe I'll put a subscript e on there and say a little bit about what that is in case your textbook has something different. And what I'm actually going to find is a little differential dE. We'll get into that. We're going to assume that that differential E is caused by a differential charge. And then usually there is an R hat. Instead of the unit vector, I'm going to put the full vector over R cubed. And we'll get into that. So usually you just use a simple R if you have a point source. But here we have an extended source. And what little curly r stands for is the observation position minus the source position. Okay, so there's an origin somewhere. And of course, we're going to call the center of our washer the origin. So that's the O. Okay, and just to point out here, KE is the 1 over 4 pi epsilon naught UPES, as we like to call it, where I'm from. And here, we're going to make high use of the fact that this is very symmetric in the ZY plane. And our observation point is up along the x-axis. So that's our P, our observation point, somewhere on the axis. And this will work for both underneath the washer and above on top. We won't get too hung up about what's going on there. Let me get a straight line there. Almost a straight line. Okay. Yeah. So that's supposed to be right over the origin. Let's tilt it a little bit. If we can. Yeah, sometimes getting the drawing right is the hardest part. Okay, so our observation point is up along the x-axis. And like I said, it doesn't matter whether that is beneath the washer or above it. Its coordinates are x, 0, 0. And in the plane, we've got our source point. I'll just grab one of those little points. Maybe color it red so we can see it. So our source is inside the washer. And it has coordinates 0, y, and z. And I'm going to put primes on those because what I'm going to indicate is when we find our total electric field, which comes about through superposition, we are going to have to integrate over the source points. So we're really using superposition with the idea that the number of points creating the electric field are infinitesimal and all buried in that source. Okay, so we can write down what this goofy looking R looks like. It is x minus y prime minus z prime. Okay, now for some simplification. The electric field is going to cancel in the YZ plane. Why? Because we have a uniform charge distribution. If it were not uniform, we would have to worry about the source doing some interesting things going around that washer. But because of symmetry, what we can basically say is that the only electric field component that matters is the X component. And we can write that down as X, which is the observation point. And then we are going to put the magnitude of curly R is just the sum of the components squared. And furthermore, I'm going to use the symmetry to simplify the plane. Those are going to be equal to another R squared. And little r, okay, we're getting a lot of r's, I know, is some radius on a circle in the plane. So little r is circular radius in the YZ plane. Okay, and because of the symmetry, your radius is constant for your two coordinates. Okay, so let's see. Now we can put in our denominator here is x squared. It doesn't look very pretty. X squared plus little r squared to the 3/2. And we're almost there. I am going to write, so usually you can write dq is it's a continuous distribution. You can write it in one of three ways, with a linear charge density times a linear coordinate times a surface charge density times a differential area, or if it is a solid object, it is a volume density times a d volume. And we could figure out, I'm not going to plug this in because it looks kind of messy, but we could figure out what our surface charge density is because it is uniform. So we could actually say that the surface charge density, yeah, I'm going to make a little table over here of fast facts. Sigma is the total Q, we'll call that Q total for TOT for total, over the area of the annulus, which is simply the difference between two circle areas. Pi R2 squared minus R1 squared. Okay, and if we needed to, we could plug that in, but I think it's easier just to leave it as a sigma. So we're about ready to integrate. The sigma is constant, so it comes out. The x is not the source. Remember, the x is the observation point, and so it does not get integrated over. And it looks like the main variable we will be integrating over is the r. And we're almost there, except we need a little differential area. And we're going to use symmetry to make that really quite easy. There's different ways to do this. But what we're really thinking about is a contribution from a subring within the ring. Let me see if I can draw it. It's not going to be real pretty. Okay, so that's not very circular, but hopefully you'll get the idea, is that little blue annulus sitting inside the real washer is our little differential area. And it has a value equal to the circumference of that little circle, which will depend on the radius, which is our little variable r. I almost need a different color at this point. And it has a width of dr. So that's the length times the width for that little differential area. Okay, so yes, we are going to be integrating over those rings, and the coordinate that gets integrated over is our little r, which goes from r1 to r2. So yeah, we're finally ready to do the integral. It never pays to go through these really quickly. Phooey, there's a 2 pi in there. Let me get that. Yeah, there we go. Okay, so we need a 2 pi from the differential area. So dA is 2 pi, coordinate dr, r. Okay, at this point, I don't know if you want to see how to integrate that, but it does look like something that you can do a simple substitution. And I'll just make a note of what that is and show you what I come up with. You better check it, though. I usually drop factors of 2, just accidentally. But make a sub with u equals 2x squared plus little r squared, and then du is equal to 2r dr. Maybe I better go ahead and do that integral. Just one more check on my math. Not a math whiz by any means. Okay, so finally what we're doing is we're finding the EX. And the important thing so far, yeah, there's going to be some junk coming out of that integral, a constant more or less. But the important thing to note at this point is that okay. So I think the integral winds up to be 1/2 the integral of u to the minus 3/2 du from one limit to the other. We'll just say limit 1 and limit 2. I don't feel like substituting the limits. I'll get it back into some other form before I fiddle with it. But the important thing is that the electric field is proportional to x. That is, that x came out. And that's a valuable thing to note. Now, there will be x's in the limits, which is why we want to write out the full business. Yeah, I think I got that integral right. So yeah, let me put in the limits and we'll see where to go from there. So there's the constant stuff out front. And like I said, you could replace those with other things. And then we have x and minus u to the minus 1/2, which is the same as 1 over square root of x squared plus r1 squared minus Okay, and so notice that this gives a correct result in the sense that the electric field, okay, let me draw the little washer over here just from the side view. What this says is that the x component is positive when x is positive, and it is negative when x is negative, because that square root stuff in the denominator has absolute value that's positive. And that means the electric field's going to look right. It's going to point axially upward above the plane and axially downwards beneath the plane. A little bit more playing around with that. What if x is really, really close to the origin? So what if x is close to the origin? Okay, in that case, and what we really want to say is x is small compared to R1. So it's somewhere, and I shouldn't say the origin, I should say the axis. No, that's fine. X is the axis. So we're really saying it's close to the origin with x much, much less than R1. Then Ex is approximately, we can forget about the x in the square roots. These are so small that you can set them equal to 0. And there's other ways that you can maybe approximate this a little bit better. But for now, the simplest approximation is to drop those. And then you have something interesting. You have 1 over R1 minus 1 over R2, which is a positive quantity. Okay, and so here's the fun thing. Let's say that you come in and you put a negative charge as opposed to a positive one. Let's suppose that you put a negative charge right on top of the axis. So we're going to come in, put a little tiny minus q there. Okay, it will feel a force equal to minus q times e sub x. Okay, and that is a restoring force because it wants to pull, well, yeah, we probably want to keep it at the origin to begin with and then displace it by a small amount up above the axis, for example. And the electric field will pull it back down. Likewise, if you displace the negative charge on the opposite side, it will get pulled back up. That is, that disk will attract that charge no matter what. So we have a restoring force, and not only that, it is proportional to the displacement from equilibrium. And that is the condition you need for Hooke's law to hold in place. And so the system would make that charge oscillate. So reminder, Hooke's law. Force is equal to minus Ks times x. So all the cluster of constants out in front of the x is equivalent to a spring constant, and we could put that in quotes if we wanted to think about that as an effective spring constant, not a real one. And the oscillation frequency for the simple harmonic motion that arises is given by the square root of that spring constant over the mass. So the system should oscillate, and furthermore, we can extract the constants that go into the effective spring constant, the electrical stuff. So yeah, we can go pull out everything in front of the x in the force. So there is a Q, absolute value. Yeah, it's negative, so yeah. The electrical K, yeah, too many Ks. Sigma, 2 pi. And then there's this awkward 1 over R1 minus 1 over R2. Okay. So yeah, that pretty much finishes the dynamics of what would happen to a small charge near the center of this annulus that gets displaced either up or down. Looks like I'm doing abstract art here. But hopefully you get the idea that that charge will oscillate up and down the x-axis because of that restoring force.